Hello, I'm Ryousei Takano from National Institute of Advanced Industrial Science and Technology, AIST Japan. I'm very happy to join this workshop as a speaker. First of all, the demand for AI and machine learning is growing rapidly, and deep learning training is extremely compute-intensive workloads. So, big computing infrastructure is needed to address this demand. In 2018, we built ABCI, an open AI research platform, and started the operation. 2 years passed. The growth in demand continues, so we decided to upgrade it this year. Today, I'd like to talk about what are opportunities and challenges of Open AI Research Platform. Modern artificial intelligence, say deep learning, and big data are enablers of digital transformation in multiple industries. Unlike classical AI, modern AI uses a set of data and machine learning techniques to solve many different classes of problems, including smart factories, smart cities, etc. In this talk, I'd like to discuss about two questions. How can computer systems support modern AI? How can we make computer systems more environmentally friendly and inclusive? This figure shows the amount of computation required to train deep learning models has been exponentially increasing with a 3.4 months doubling time from 2012 to 2019. The growth is quite rapid compared to Moore's law, like this. What drives changes in effective compute over this time of period? The right figure is estimation of breakdown. I don't say this estimation is perfect with confidence. Here, the trend is split into Moore's law and parallelization, as well as progress in algorithmic efficiency. That means deep learning training requires more parallel and distributed computing infrastructure. In other words, AI is now a supercomputing problem. To address this problem, we started ABCI project in 2016. ABCI is large-scale and open infrastructure to push the envelope of AI research and development. ABCI has world top-level compute and data process capability, and in the latest supercomputing ranking, it is ranked 14th in top 500 and 13th in Green 500. ABCI is open. We provide a service for academia, industries, as well as international partners. We start the operation from October 2018. As I said before, we upgraded this May. ABCI Data Center is located in Kashiwa 2 campus, University of Tokyo. It is about 50 kilometers northeast from center of Tokyo. Our vision is AI infrastructure for everyone, not only top-notch researchers, but also beginners of AI. For experts, we have grandchild program. The winner can use all systems for 24 hours free of charge. For advanced and intermediate users, large enough resources is available anytime. For beginners, web-based GUI for designing deep learning networks is supported. Roughly speaking, we have 2,500 users and 360 projects on ABCI. And the external users are 86% of total number of users. the utilization and revenue have increased more than 4 times in 3 years. This is the distribution of application fields of ABCI. I'm sorry for not translating Japanese characters. As you can see, this distribution is long-tailed, and the major fields are AI algorithms, image and video recognition, natural language processing, drug discovery, etc. I will share some benchmark results. This is a little bit old result. ABCI updates the world record of image classification training several times. This chart shows performance improvement in last 4 years. Back in 2050, image classification training takes 29 hours using 8 GPUs. Training speed dramatically improved with keeping the accuracy. Sony broke a record in 2080, and Fujitsu broke it again in 2090. This means ABCI is a powerful infrastructure to compete with tech giants in this field. This is another benchmark result with MLPerf HPC that includes 2 large-scale scientific applications using deep learning. CosmoFlow trains a 3D convolutional neural network to predict physical parameters of the universe. DeepCam trains a climate segmentation model to identify extreme weather phenomena. ABCI achieves 20 times speedup for CosmoFlow and more than 12 times speedup for DeepCam compared to other supercomputers. A few next slides show some large-scale application on ABCI. FDK is a well-known algorithm to generate 3D volume image from 2D projections. We propose a distributed FDK framework to accelerate high-resolution image reconstruction by taking advantage of heterogeneity of GPU-accelerated supercomputer. Right bottom figure shows the scalability with 3 different output sizes. Using up to 2300 GPUs to solve a 4K and 8K problem within 30 seconds and 2 seconds respectively. This is an example of brain science application. In this project, we analyze small fish neural activity dataset on ABCI. Convergent cross-mapping in an algorithm to find cause and effect relationships in time series data invented by George C. Haller. However, the algorithm is NP-hard and was not very scalable. With our proposed method, MPEDM, we partially put the algorithm on GPUs. Actually, k-nearest neighbor algorithm on GPU. We ran MPEDM on ABCI with 3 datasets which are recorded from zebrafish under different conditions and different scale. The results show MPEDM is more than 1,500 times faster than original CPU-based implementation in the smallest dataset. We also analyze largest causal of whole brain dynamics at single neuron resolution to this date. Let's go into detail of ABCI system. ABCI consists of a high-performance computing system and large volume storage system, and they are connected through InfiniBand network. Behind the high-performance AI capability, there are 2 key points. Point 1, ABCI is large-scale and state-of-the-art GPU farm. GPU is nowadays good at accelerating AI processing, and we can use cutting-edge software framework and tools. ABCI has more than 4,000 NVIDIA V100 GPUs and allow users to run a large-scale AI and deep learning jobs smoothly. Point 2. We employ supercomputer-based network technologies. The communication is bottleneck for large-scale deep learning. All GPUs and CPUs can communicate each other through low latency and wide bandwidth network. In addition, we have upgraded compute nodes and storage system this year. As you can see, we added 960 NVIDIA 800 GPUs in total. Each new compute node has 8 800 cards, 2 Intel SD processors, 500 GB of memory, 2 Intel SSD disks, and 4 InfiniBand HDR adapters. Comparing with the old compute nodes, the number of GPUs had doubled, so we also doubled the capacity of both memory and storage. The theoretical peak performance reaches 225 petaflops for single precision, 850 petaflops for half precision, and over 1 exaflop for half precision with sparsity. This is a big leap from the original system. This slide compares 300 node and 800 node. At the right-hand side, this is a block diagram of compute node A. 800 GPUs communicate with each other through NV switch. In terms of form factor, compute node V is 2U height and half wide blade server, and compute node A is 4U height server. This is an InfiniBand interconnection network for compute node A. They are connected by a full bisection network, and sharp V2 is enabled, so InfiniBand switches support collective offloading. For storage system, we added 10 petabyte project storage space and 400 terabyte SSD-based high-speed storage space. I will briefly mention our software stack. We employ container-based software stack that allow users to fully customize their own software environment. The administration team is updating basic software library and tools with short cycle, and the user can choose the combination of software components in their container environment. This is a very preliminary performance evaluation of ABCI 2.0. Here we show small-scale experiments using image classification training benchmark. Node V is the original V100-based node, and node A is the new A100-based one. In the middle figure, A100 has almost double performance of V100 with single-node training. The right figure shows the performance of multi-node training and the scalability. From the viewpoint of scalability, Node A is relatively lower scalability. This may be because the performance tuning of software stack is not doing well. In the case of deep learning, we typically have two approaches of parallelism: data parallel and mode parallel. Parallelism strategy is very important for large-scale training. We develop ParaDL, performance estimation model, and a tool for predicting performance of large set of configuration for distributed training at scale. We improve the estimation accuracy in several ways. I don't go into the detail. We demonstrate up to 97% correctness and 87% correctness on average. Our future work is to find new fine-grained hybrid parallelism models. This is another research work. Convolution is a fundamental operation on image processing as well as deep learning. We propose an efficient 2D convolution algorithm by taking advantage of register cache in GPU. Register is faster than shared memory, but the register is limited hardware resources. So we carefully design software systolic arrays combining a few register cache and shared memory. We demonstrate better scalability and performance improvement compared to existing state-of-the-art convolution libraries like ArrayFire. I'm going to go to the next topic. AI research can be computationally expensive, and energy efficiency and CO2 emission become more important in the future. For example, right figure shows CO2 emission of a large-scale training is 5 times larger than lifetime CO2 emission of a car. This is a big issue. So there are opportunities for efficient improvement at each level, including algorithms, processor, data center, and energy mix. In the algorithm improvement, green AI is beginning to attract attention. Recently, Google researchers report large but sparsely activated neural network can consume smaller energy without sacrificing accuracy, despite using as many or even more parameters. In this workshop, many audiences may have interest in processor improvement, for instance, domain-specific accelerators. But next slide, we will show our work on data center improvement. We designed ultra-green data center for ABCI from scratch. GPU is power hungry and generates lots of heat. Cooling is a challenging issue in this kind of data center. This is the layout of our data center. There are 2.5 cooling pods in the server room. We built cooling pod directly on concrete slab. There is no free access on the floor. Passive cooling tower and active chiller are located outside. We apply free cooling for all year and introduce direct liquid cooling using warm water, say 32 degrees Celsius water in summer season. We isolate hot aisle and cold aisle for efficient air cooling. Cooling capacity is 3.2 megawatt. Power capacity is 70 kilowatt, 60 kilowatt by water, 10 kilowatt by air. As a result, we achieve very energy efficient data center, and average PUE is under 1.1. Let me summarize my talk. AI is now a supercomputing problem. ABCI is open and large-scale infrastructure to push the envelope of AI research and development. There are a lot of opportunities and challenges in this field. For example, parallelism strategy is important. We developed ParaDL that is guiding a parallelism strategy on a given system. And also, in terms of sustainability, improving energy efficiency and reducing CO2 emission become more important in the future. Thank you for your attention. I'm happy to have your questions and comments.